Wang. I'm a PhD student in the Integrated MEMS Laboratory under Dr. Ayazi at Georgia Tech. Before I start, I'd like to apologize for not being able to attend the meeting in person due to my visa issue. It's my great pleasure to present this work on behalf of all the authors on self-bonding piezoelectric micromirror designed for integrated atomic beam devices. Since the dawn of humankind, the research for process timing and frequency standard has always been important across the art of technology advancement. Today, chip-scale atomic clock is now commercialized and serves as frequency standard in many cases. These products are so accurate that two of such clocks would differ by less than 1 second over the age of the universe. For example, a commercial CSEC from Microchip is 4 per cell and has a typical Allen deviation of 10 to the power of minus 10 range with buffer gases. These products are also very expensive because of the manual assembly. Our work has demonstrated if we introduce a laser to access the atomic beam, it will make the Allen deviation down to 1.2 times 10 to the power of minus 10. In this figure, the atomic beam is produced by heating the atom reservoir to make the rubidium vaporized. Then the rubidium vapor is going through cascaded collimator to produce an atomic beam and intersect with the laser to access the atom from ground state to higher energy state. This configuration requires a collimator and a parallel structure for laser to travel, which increase the cost and makes assembly work even harder. In order to reduce the manual assembly effort, meanwhile bring the cost down, one solution is to build a fully integrated atomic beam clock. This figure shows the configuration of next-generation atomic beam clock. There are two 45-degree micromirrors facing to each other, integrated with a collimator, where a rubidium ampule behind the collimator is heated to generate the atomic beam. Two lasers, shooting and being reflected by the laser, will interact with rubidium vapor in the center. The first laser beam, which we call state preparation, is used to excite the atom, and the second laser is to monitor the performance of clock, referred as readout. This system has near transit time limited line widens without using buffer gases. Buffer gases is commonly used in vapor cell to increase the coherent time, but they can induce long-term drift and the aging of the order of 10 to the minus 9 per month. Compared to our previous work without using this micromirror, the inducing a lot of assemble work shows a limited detection efficiency and poor SNR. With 45-degree tilting mirror, the improvement on better collection efficiency and signal-to-noise ratio could potentially make the instability down to 6 times 10 to the power of minus 11, as our recent measurement shows. This figure is the Allen deviation of the atomic beam clock. After finding the atomic spectrum, a modulation and demodulation technology is used to lock in its peak in the saturated absorption spectrum. The output signal is then used to calculate this Allen deviation. The picture on right shows our previous work. On right top, we use KOHH mirror, which had a poor optical performance as well as 54-degree tilting angle. On bottom, we assembled the mirror with collimators. The angle was well controlled but had a poor reflectivity of 95%. The optical performance of KOHH mirror was 100 times degradation compared to commercial mirrors. Another reason for QHH mirror doesn't satisfy for atomic beam application is the input laser and output laser will intersect with each other, makes the readout impossible. As for assembled mirror, the mirror was easily damaged given a poor reflectivity. This work we will provide. One key factor to have a good optical performance micromirror is to build the mirror on a well-finished surface with low surface roughness. As an example, current commercial mirror has a global surface roughness less than 4 nanometer in 1 millimeter range. Our previous QHH mirror shows a 450 nano global surface roughness and 50 nano local roughness as the OPM measurement shows on the right top. This work, on the other hand, which is built on a mirror finished surface silicon, shows a less than 10 nanometer local roughness as the AFM measurement shows. Here is the overall design. As we mentioned, the mirror should be built on a finished surface of silicon. It was then actuated and assembled in place electrically, which enables the possibility of large-scale manufacturing and reduce the cost. The actuation relies on aluminum nitride deposited on silicon and the electrostatic force, which improves the controllability of the whole process. The mirror widens can be tolerated to square root 2 times SOI wafer thickness to achieve a final tilt angle of 45 degrees. Here, in the figure, we have two mirrors integrated with the collimator. The mirror is then actuated and held it at its bending position, followed by a current running through the heater on the substrate. The heater can provide temperature environment for local gold to silicon eutectic bonding to happen. From console simulation, the structure exhibits a torsional resonance mode at 1.4 kHz, with tilting sensitivity of 2.25 degree per volt. Meanwhile, as simulated point curve shows, a 49-volt DC voltage is required to provide sufficient electrostatic force to trap the mirror by underlying gold with piezo actuation, and 80-volt is sufficient to pull the mirror down to a 45-degree position without need for further piezoelectric actuation. Here is the result of fabricated micromirror using MEMS technology. The most important component is the torsional bar, as marked here. Those torsional bar provide torsional motion as well as anchor after bonding. Each torsional bar on the same side spaced at 200 micron to provide extra token during the actuation. The folded shape of torsional bar can significantly reduce the stress during large angle movement and make the final bending angle more accurate. The main difference between the piezo mirror and non-piezo mirror is the final DC voltage used for keeping it at 45-degree position. With strong piezo effect, the required electrostatic force would be smaller, resulting in a lower DC voltage used in this process. It can make the cost even lower during the large angle manufacturing. Here is the process flow. We begin with aluminum nitride on silicon substrate, which consists of a 200 nanomobidium layer deposited on top of 1 micron aluminum nitride film. The mobidium and aluminum nitride layer are then patterned to define the driving beam. Next, a 20 nanochromium adhesion layer is deposited, followed by a 100 nano gold layer evaporated to form the reflective mirror surface. The 14 micron thick silicon device layer is then etched using ICP to define the torsional bar. Finally, the handle layer and the box layer are selectively removed using Bosch process and HF etching respectively to create a fully suspended structure. Then we took two of such mirrors and attached them to the substrate. Next, we drive the piezo layer to make the mirror oscillating. As the gap between mirror and the substrate decreased, we then perform trapping and bonding process to get the configuration with two 45-degree mirrors facing to each other. The frequency spectrum is shown on the right-hand side for voltage measurement from sensing electrode integrated with aluminum nitride beam when a 1-volt peak-to-peak voltage is applied. The animation shows the mode shape of torsional mode right here. The result shows the first bending mode occurred at 1.8 kHz, and the primary torsional mode, as shown here, is 2.3 kHz. The mechanical quality factor, or Q factor, is measured at around 10 under atmosphere. One possible improvement for the future design would be increase the Q factor. Q is proportional to the maximum oscillation angle from piezo effect. The larger angle means the smaller gap size between mirror and its substrate, which will bring the DC voltage required to trap the mirror down even smaller. Next, the mirror is bound to a silicon handle layer, which has a gold layer evaporated onto its surface for trapping purpose. Given the torsional mode resonance frequency, the mirror is driven by applying a sine wave voltage via op-amp to aluminum nitride beam, inducing oscillation through piezoelectric effect. As mirror oscillates, the gap between its edge and the underlying gold film decreases until gold film on the silicon handle layer could capture it through electrostatic force. During this process, a current is passing through the serpentine gold, heating it up to 390 degrees Celsius, which will provide the environment for gold-silicon eutectic bonding to happen. Maintaining contact with silicon surface will ensure a permanent eutectic bonding. Here is a little bit more detail. On the right bottom, the substrate had both serpentine gold as heater and a bonding plate. They are all made of gold. On left-hand side, when applying voltage, the mirror is first bent and hold at its position. As you can see, the light is changing in this picture. Then a current is going through the heater. As you can see on the right top, the gold heater is working and it gets red. After 45 minutes contacting, the gold from bonding plate and the silicon under the mirror will interact and bond together. The final result of one-sided mirror is shown on the right-hand side. Then, if we do the same thing to another side, we eventually get our configuration that has two 45-degree mirrors facing to each other. This SEM picture shows the result of gold-silicon eutectic bonding. The left figure is the bonding area of mirror and the substrate. The right figure shows the substrate after the mirror is removed. There is a very clear trace in the center where is the bonding area. On this trace, there is a mirror component left over, which proves the bonding is very strong. The angle and reflectivity was then measured by directly shooting a laser onto the device, and the reflected laser is then detected by the camera. The angle is directly measured by the camera, and the reflectivity is calculated by dividing the reflected laser power by input laser power, as this figure shows. The figure shows a bending angle of 44.7 and the reflectivity of 99%. The slight deviation from ideal tilting angle and the less perfect reflectivity can be attributed to warpage of the mirror and the structure inaccuracy during the fabrication. In order to prove the designed mirror meets the requirement for atomic beam clock and will keep functioning during the high-power lasering, more work has been done in structure instability analyzing from console simulation, where we're shooting the laser onto the mirror surface and calculating temperature changing as well as the thermal stress gradient between gold surface and the silicon underneath. As the result shows, as laser power increased, the temperature is not changing too much, only increased by 0.015 degrees Celsius, which results in a very small stress gradient. So the curvature happened in the mirror is also neglectable, as this table shows. To sum up, overall structure is satisfied for atomic beam device experiment. We then set up the high-power laser test for the mirror by putting the mirror under 1 watt laser for a week long. This test doesn't change the bending angle as well as the reflectivity, as the right figure shows. The surface is still very shiny after 1 week lasering and the bending angle is not changing. In summary, this work successfully achieved a 45-degree tilted micromirror with excellent reflectivity at a designed bending angle. It's able to produce a micromirror with any bending angle. It also paves the way for wafer-level fabrication using MEMS technology. The mirror can be used as a crucial component for a fully integrated atomic device. The mirror itself also shows a potential as a scanning mirror. Our next step gonna be build integrated atomic beam clock and test its performance. Also, the optimization for mirror design would be implemented for future atomic beam clock application. Here, authors want to thank Xinyu Jiang and the Institution for Matter and System at Georgia Tech for helping and discussion. This brings me to the end of my presentation. Thanks so much for your attention. Since I was not able to answer your questions at this time, feel free to reach out to us via email with any questions or comment you may have.